In this lesson, we are going to look at standing waves on a string. To understand standing waves on a string, let's first look at some properties of waves. This is a pulse moving toward right, and here is a fixed end. Now this pulse is going to reflect from this fixed end. Let's see its reflection. When a pulse is coming toward a fixed end, after reflection, it is turning upside down and it reflects like this. If we have a free end, on the other hand, when the pulse is approaching to the free hand, its reflection from the free hand will be upright. And the second property of the waves is when a wave traveling, for example, toward this direction, and another wave reflected from the, for example, fixed end, and it is upside down, it is moving toward that direction. Once they overlap, they cancel each other and they destroy each other. The string appears like a straight line. Similarly, when two waves, one of them is approaching upright, and if it is, for example, reflected from a free end, now the wave moving toward right and the wave moving toward left, now they are going to now reinforce each other, and there's going to be some constructive interference, and they're going to reinforce each other. The amplitude of vibration will increase. Okay, now let's look at the standing waves. Assume a wave is approaching a fixed end. This is the wave traveling, and some of the waves have already reflected from the fixed end. Now this wave traveling to the right and the wave traveling to the left, they are now going to interfere, and they are going to at some points they are going to reinforce each other, at some points they are going to destroy each other. So now assume this is the light ray moving toward right, this one, and this one is moving toward left, and this is the incident light and this is the reflected light. As you see, their wavelengths and amplitudes and frequencies are completely the same. So I have made it a little bigger here. Now once they meet each other, they are going to form a new wave of this amplitude. The amplitude of the composition of the two waves increases, and this is called a standing wave. And these points are called antinodes. These are the antinodes, and there are some fixed points, such as this point, this point, this point. These points are nodes, and these points are antinodes. We will use them in our problem solving. To better understand the standing waves, it will be better to go an animation. Now let's start the animation. I will explain what's happening. Now here is a vibrator. It is vibrating up and down, and the waves are produced and pulses are produced, and they are traveling toward the right. Here is a fixed end. Now the waves are going to reflect from this fixed end, and the incident waves and the reflected waves are going to interfere, and a new shape of the string will appear. Now as you see, now the reflection happens, and the reflected ray is shown with blue color, and the incident wave is shown with the red color, and the composition of the interference of the two waves, the one which is moving to our right and the one is moving to our left, and they are making such an interference pattern in which the amplitude increased. So as you see, when the incident wave and reflected wave have the same frequency and wavelength, they produce a standing wave. As you see, these black dots, the wave made with the black dots is a standing wave. And as you see, some points, for example, this point is called N. This is a node. It is not moving. This point is not moving. It's also N. This is also a node. This is also a node. On the other hand, this point, this is an antinode, and it is moving up and down. So as you see, this wave is not traveling. The wave which is shown with the black dots, it's not traveling to the right or the left, but it is just oscillating up and down. But the blue one is moving left and the red one is moving to the right. Their interference is a standing wave, and it is not moving, just it is oscillating up and down. Okay, let's go to our presentation. So let's look at the different type of standing waves in a string. Assume we have a string between 2 points. It is fixed, both ends are fixed, and the length of the string is L. The smallest possible wave that we can produce between two fixed point is a half wavelength. You can produce such a wave between two fixed points, and it is going to oscillate up and down. As I showed in the animation, this point is an antinode. It will move up and down. These are nodes, they are fixed points. This will be a smallest standing wave. So as you see, the length is L, and here the smallest wavelength I am going to, by the smallest I mean this is actually going to be the largest wavelength, lambda 1. I'm going to call it lambda 1 will be equal to actually lambda 1 over 2 will be equal to L, because this is a half wavelength. So from here we can write that lambda 1 is equal to 2L, and we know that frequency is equal to V over lambda. Then from here we can say the frequency of this oscillation F1 will be equal to V over lambda 1, and it will be equal to V over 2L. Why? Because lambda 1 is 2L. Let's look at the second one. As you see, this is a full wavelength, and lambda 2 will be equal to L. So from here we can write that F2 is going to be equal to V over lambda 2, and it will be equal to V over lambda 2 is equal to L. This is F2. What about this one? Here we have 1.5 wavelength, so we can write 1.5 lambda 3 is equal to L. So from here we can write lambda 3 is equal to 2L over 3. So then frequency F3 will be equal to V over lambda 3, and it is going to be equal to V over, instead of lambda 3 I am going to write 2L over 3. I am going to write 3 here. Okay, so now here let's see, F1 is equal to V over 2L. What if I multiply this one with 2? If I multiply this one, these 2 and 2 will cancel each other. I will get V over L. It means that F2 is equal to 2F1. Similarly, if I multiply this one with 3, it will be 3V over 2L. I will get this one, and it is F3. So F3 is 3F1. So F4 will be 4F1. Let's see it. Here we have two wavelengths. So 2 lambda 4 equals L. And lambda 4 will be equal to L over, sorry, it will be L over 2. And from here F4 will be equal to V over lambda 4. So we will get 2V over L. And this is also going to be equal to 4F1. So let's summarize all of these findings. As you see, this is called F1 is called fundamental frequency, and this is called lambda 1 is fundamental wavelength, and this one is called first harmonic. This is called second harmonic, third harmonic, and fourth harmonic. So let's find some formulas. As you see, this is F1, and this is 2F1, 3F1, 4F1. So for F, for the frequency, we can write Fn is equal to n times F1, where n is equal to 1, 2, 3. Okay. Similarly, Fn is going to be equal to V over lambda n. Why? Because as you see, F1 is equal to V over lambda 1. This is V over lambda 2. This is V over lambda 3, lambda 4. So we can write Fn is equal to V over lambda n. And one more, we can write lambda n can be equal to lambda 1 over n. See, lambda 1 is 2L, lambda 2 is L, lambda 2 is lambda 1 over n. It means lambda 1 over 2. Lambda 1 is 2L, divide by 2, we are going to get L. Okay. Similarly, lambda 1 is 2L. If I divide it by 3, I will get lambda 3, 2L over lambda 3. Similarly, I can get lambda 4. So this formula is also valid. One more, Fn can be also equal to the Nv over 2L. As you see, F1 is equal to V over 2L. And F2 is going to be equal to, it is equal to V over L. And this is equal to 3V over 2L. This is equal to 2V over L. So once you multiply this one with 1, 2, 3, 4, if you multiply with 1, we are going to get F1. Let's multiply this one with 2, we are going to V over L. Let's multiply with 3, we are going to get 3V over 2L. So this formula is also valid. Now we are going to use these formulas to calculate some problems, some questions.